Hello, it's Mrs. Allison. Today we are going to look at sequences. And like I said before, if the last 2 years had been a perfect world, this is something that should be a bit of review. I know that the last few years have not been perfect, so therefore we're going to go through this quickly. So if you need to hit pause and process through some of this, feel free to do so, or slow the video down, that's fine. But we are going to talk about sequences. What we're going to focus on this chapter happens to be infinite series. And to begin that discussion of series, we really need to backtrack into the idea of sequences and what a sequence is. So let's begin. A sequence, notated as A subscript n. So you will often hear me say A sub n. I am saying A subscript n. So a sequence is an ordered list of numbers. And the ordered list of numbers goes A sub 1, then A sub 2, and A sub 3, all the way up. It just keeps going. And what these little subscripts mean is they represent the term number or the place in the sequence that value is. Okay, there's two ways that we can define sequences. Sequences can be defined using either a recursive formula, or you may hear it referred to as a recurrence relation. And basically what that is you need a term. Once you know one term, then you can find each subsequent term. So each subsequent term is based on the term before it, or the previous term. So you may see it notated this way: A subscript n plus 1, meaning the n term plus one more, can be found by plugging in the A sub n term to the function. Okay. Or sequences can be defined explicitly. And explicitly just means that if you substitute n, you can find the nth term. So if I want to find the fifth term, I plug in 5. And that's what this looks like. A sub n, so the fifth term, you get when you plug in 5. Now, I can't do that with recursive. With recursive, I have to know the term before. So if I wanted to find the fifth term, I would have to know the fourth term, and then the third term, and then the second term, and then the first term. So each of these sequences has a domain that is the set of positive integers. Okay, so each subscript that you'll see is a positive integer, typically starting at 1, sometimes 0. So the 0th term, the first term, the second term, etc. The subscript notation is used to identify each member of the sequence. So A sub 1 represents the first term. A sub n represents the nth term. And then the entire sequence is represented with those curly brackets. I know there's an official name. I'm not sure what it is, but these braces, these curly brackets, represent the entire sequence. Okay. So let's go through some examples and then some definitions as we go, just to see if we can reiterate some of these ideas. If you are asked to list the first 4 terms of the explicitly defined sequence, it means that I can plug in 1 and find the first term. I could plug in 27 and find the 27th term, and I don't have to go through 26, 25, 24, 23, etc. So the first 4 terms of the explicitly defined sequence literally means that I'm going to plug in 1, and I'm going to plug in 2, and I'm going to plug in 3, and I'm going to plug in 4, and get those first 4 terms. So here's what that might look like. So the first term, A sub 1, we find when we plug in 1 for n. 2 minus 1 is 1 over the denominator of 2. So the first term, the A sub 1 term, is 1/2. The second term would be 2 times 2 minus 1, over 2 plus 1. So 4 minus 1 is 3 over 3, or 1. And I can keep going. So the third term, we get 2 times 3 minus 1 over 3 plus 1. So 6 minus 1 is 5, 3 plus 1 is 4. And the fourth term is 2 times 4 minus 1 over 4 plus 1, which equals 7 over 5. Oftentimes when you see this represented, it will just be a list of numbers. So 1/2, comma 1, comma 3, oops, that's a 5, 5/4, 7/5, and this would be our ordered list of numbers. Now, you will also probably see this with the curly braces, and since it only asks for the first 4 terms, this is sufficient. I don't need to include any additional terms. So why don't you hit pause and try finding the next 4, or the next example, that B sub n. All right, hopefully you had a chance to go through these. I get for my ordered list of numbers, the first 4 terms in this sequence would be 1 3/4, 7/9, and 15/16, and then it would just keep going from there. How'd you do? Great. Okay, let's look at a recursively defined sequence and see what I mean about finding the terms before it. If I'm going to find the first 4 terms of a recursively defined sequence, there is one key piece of information that I must know. I must know at least one of my terms. If I don't know that term, I cannot continue on. Now, the beauty is, in the first 4 terms, I've already got one of the 4. So a sub 1 is -1, but let's look at finding a subscript 2. This says, according to the formula, I'm going to do 2 times a subscript 2 minus 1. So a subscript 1 plus 3. You can see that from this very definition, I need to know the term before it. So I need to know that -1. So 2 times -1 plus 3 gives me -2 plus 3, which is 1. And then I'm going to continue on that pattern, a sub 3. I would need to know 2 times a sub 3 minus 1, which is 2, plus 3 to be able to solve this. So we would have 2 times the term before it. Well, the term before it was 1 plus 3, which gives me 5. And then to find my fourth term, I would need to do 2 times the term before, which was 5, plus 3, which gives me 13. So my ordered list of numbers here would be -1, 1, 5, and then 13. So hit pause and see what you can do on this next one. All right, hopefully you had a chance to try this next one. And if I were to find my first terms, you'll notice I need the term before. Now this one's set up a little bit different just in how it looks. My b subscript 1 is 5, but notice the next term says k plus 1. So if I substitute in and I want to find b sub 2, that means k had to be 1, and so therefore the k that is 1 goes in here, and then I'm using the term before. So I would have 1 plus 1 over 2 multiplied by the b sub 1. That's what that looks like for this particular problem. So here I would have 2 over 2 times the first term, which is 5, which gives me 1 times 5, which is 5. Now do it again. B sub 3. B subscript 3 would be like saying 2 plus 1 over 2 times b sub 2. I know b sub 2 is 5, so I would have 2 plus 1 over 2 times 5. That would give me 3 over 2 times 5, or 15 halves would be b sub 3. And then I would continue again to find b sub 4, and hopefully what you got, b sub 1 is 5, b sub 2 is 5, b sub 3 is 15 halves, and hopefully when you plug in 4, the fourth term, you see that the fourth term is 15. All right. Now, sometimes we need to be able to write a rule or a function that gives us the first, or that gives us the terms of the sequence. We often refer to this as the nth term of the sequence. Now, the nth term of the sequence is typically defined explicitly, meaning it looks like an equation where we can just substitute in n to find a value. Now, some people are really, really good at finding these patterns. They can see patterns right away. Some people it takes a little bit more work, and that's okay. we're going to try trial and error on these to see if we can develop a rule that will give us these terms as a sequence. So let me show you, for example. One of the patterns that you can look for when you're writing an nth term, when you're writing a formula. Now, an nth term or a formula looks a lot like what we had here. This would be defined recursively, or a recurrence relation. This would be defined explicitly. So one of these two is what I'm looking for. We're actually going to do both. The recurrence relation or the recursive formula is usually a little bit easier because if we can look for patterns that happen, it's easy to go back and write how it impacted the one before it. So, for example, do you notice in this pattern right here, this first one, that as I go from 1 to -3, and then -3 to -7, and then -7 to -11, do you see what's happening there? Each time I'm subtracting 4 from the term before it. So if we were to define this recursively, meaning using the term before, I would start with the fact that the first term is 1. And then I would say, from the first term, any other term, otherwise known as a sub n, equals the term before it, so a sub n minus 1, one less than the one we had, a sub n minus 1 minus 4. I'm just taking 4 away from any of the terms before it. This would be defined recursively. Now, if I want to define this explicitly, I need to think a little bit differently. If you see a pattern where we're subtracting 4 every time, or we're adding 3 every time, or if we're adding or subtracting a repeated number every time, this is like a multiplication, meaning I'm going to be multiplying my variable by this 4 or this -4, or this 3, whatever it happens to be. My case is -4. So think linear for a second. This is like having a slope of -4. So my equation might look something like this. A sub n equals -4 times n, meaning each time I'm gonna increase it by a -4. So if I tried n right now, and I plugged in a sub 1, what I should get if I plug in a sub 1 here is I should get 1. Well, the problem is, if I plug in 1 right now, I get -4. That's not the same as 1. Okay? Or if I plug in 2, I should get -3, and I definitely don't get -3 when I plug in 2. So is there something I can add or subtract to this number that will get me back to where I started, or the sequence that I have? Well, if I add 5 to each of these, let's try it. If I substitute in 1, I should get 1 back out. -4 times 1 is -4. -4 plus 5 gives me +1. Great, but don't assume that that's the answer until you check a couple more. Like, let's say I plug in 4. If I plug in 4, I should get -11 as an answer. -4 times 4, the fourth term, would be -16, and -16 plus 5 is -11. So this is what we call our explicit formula, or our explicitly defined formula. Sometimes the explicit one requires a bit more trial and error. So, if you're feeling brave, try the next few and just see what you do. So brainstorm, work with your neighbor, whatever you'd like to do with this, hit pause, and then come back and check those. See, patterns can be fun. Sometimes we're really good at them. Sometimes it takes a little bit of time to think about it. So let's look at some techniques that we can have. Notice that this next one alternates between a negative and then a positive, and then a negative and a positive. Can you think of any way to make something alternate? All right, to make something alternate. If we want to alternate terms, alternate the signs of terms, what we're going to do is we're going to do a -1 raised to the n power. So negative 1 raised to the n power is going to alternate signs. Okay, so what else is happening though? Did you notice that in the denominator, it keeps going up? Maybe we even rewrite this first term as negative 1 over 1, and then 1 over 1/2, and then negative 1 over 3, and 1 over 4. Do you notice that each time it's going up by the factor of n? So it's just n. It's the value of n. So this expression would be negative 1 to the n power. That would be my explicit form, and that's the one we're really looking for when we ask for an nth term. All right, what about the next one? Would it help you, or did you notice that this term of 1 over 8 is really equivalent to root 4 over 16? Because root 4 over 16 is 2 over 16, and 2 over 16 is 1 over 8. If that helps, hit pause and see if you can try it, and we'll move on. All right, do you notice it? I see a square root of n in the numerator. And then do you notice that each of the denominators is a factor of 2, or is a power of 2? So 2 squared, 2 to the third, 2 to the fourth. So this would be 2 to the n power, would be my explicit definition. All right, anybody come up with this last one? This one's tricky. What sort of functions do you know that bounce between 1, 0, negative 1, 0, 1, 0, negative 1, 0? If we were to look at this, it might look like this. The first term is 1. The second term is 0. The third term is negative 1. The next term is 0. Then positive 1. Then 0. Then negative 1. What sort of function do you know that looks like this? Hopefully what you said is sine. This does look like the sine. So this is a sine function. So this would be a sub n. My nth term is a sine function. But sine of what? How can I make sure that the only numbers I get are 1, 0, negative 1, 0, 1, 0, negative 1, 0, etc.? Well, if we do this as pi n over 2, that will get us there. So these are our explicit rules, our nth term definitions. All right. So why or how does this tie into what we were doing before? Well, now we're going to focus on, you guessed it, the limit of a sequence. So we're going to begin to look at limits as they relate to sequences. So we're going to be looking at sequences that are said to converge, meaning the terms of a sequence approach what we call a limiting value. Okay, so we can define a sequence such that the function f of n equals the sequence, meaning we have an nth term definition. We have defined the formula for this sequence. Then we can say that the limit as n approaches infinity of that sequence is L. If it is in fact L, then we say the sequence converges. Now, a sequence that oscillates between values, so bounces between negative 1 and 1, like we've just looked at, that sequence diverges. It does not converge. Or if 1 shoots off to infinity, then we say it diverges. Okay, so let's find the limit of each sequence if we know the nth term or the formula that is given. All right, looking at this first example, if I were to find the limit here, here's what I'm looking for. The limit as n approaches infinity of 1 plus 1 over n to the n power. If I substitute in right now the limit as n approaches infinity, what do I get? hopefully what you notice is I get the indeterminate form. I get the indeterminate form of 1 to the infinity power. That's a problem, which means I need to do some work. So remember, before I can get it L'Hopital ready, I need to be able to turn it into a form that can do that. So with 1 to the infinity, the first thing that I'm going to do is I'm going to take the natural log of this limit. So this is going to be the limit as n approaches infinity, and then I'm going to take the natural log of this expression of 1 plus 1 over n raised to the n power so that I can use this natural log to bring the n down. And what that looks like is the limit as n approaches infinity of n times the natural log of 1 plus 1 over n. Now, if I try the limit now, I brought it down, I'm going to check it. The problem is I get infinity times 0. So 0 times infinity, infinity times 0, that's still an indeterminate form. So I still have more work that I need to do. So the next thing that I'm going to do when it's 0 times infinity, remember the technique that we're going to use is we're going to change one of them to a fraction. So I'm going to rewrite this as the limit as n approaches infinity of 1 plus 1 over n over 1 over n. Now this is L'Hopital ready. When I plug in infinity here, I get 0 over 0, which means I can use L'Hopitals now. So using L'Hopitals on this, we get the limit as n approaches infinity, and the derivative of the top is a bit messy. Oops, I lost my natural log up there. Is 1 over 1 plus 1 over n times the chain of that, which is negative 1 over n squared. And the derivative of the bottom is negative 1 over n squared. Now, it's kind of nice because those two will cancel out. Now, if I go to take the limit as n approaches infinity of 1 over 1 plus 1 over n, really what I'm getting is 1 over 1 plus 0 as n goes to infinity. And the beauty of that is that's just 1. So I know the limit of this sequence is just 1. All right. I gave you one that's not so bad, the next one. So hit pause and try this next one. Okay, hopefully if you look at this one, really all I'm doing is taking the limit as n approaches infinity of the cosine of 1 over n. And if I substitute in an infinity or use the idea of infinity, really I'm taking the limit as n approaches infinity. Oops. I don't really need the limit anymore. If I substitute in infinity, I really just have the cosine of 1 over infinity, not a thing. So we'd say the cosine of 0, because 1 divided by infinity is as close to 0 as we're going to get, which gives me a result of 1. So I've just found the limit of the sequence. All right. The next two examples ask you whether the sequence converges or diverges. So hit pause and try these next two examples and just see how you do. And then we'll come back. All right. Hopefully you had a chance to try these examples. So if we're looking for the limit as n approaches infinity of, for this first one would be 5 plus negative 1 to the n power. What's the problem here? Well, we know this limit doesn't exist because it oscillates. Therefore, this diverges. So there's very little work that needs to be done once I know it's an oscillating function. All right, what about the next one? How'd you do? Well, hopefully you noticed on this next one. Well, let's write the problem first. This would be the limit as n approaches infinity of 2n over 1 minus 3n. You guys, this is a rational function. And sure, I could use L'Hopitals because this is L'Hopital ready at this moment. But the problem is, I know the rules for this. I know when those degrees are the same, really all I care about are these terms here, oops, that was supposed to be a highlighter, are these terms here of 2n and negative 3n. And I know the limit of those because one, when we go to infinity, is really not going to impact this any. And I know as I go to infinity, the result of this is just going to be 2 over negative 3. So we can say that this converges because the result is finite. Okay, sometimes we may need to use L'Hopital's. So it is possible to have to use L'Hopital's. So hit pause and try these next two and see what you come up with. All right, hopefully you've had a chance to look at these ones. If I substitute in here, let's rewrite the problem, the limit as n approaches infinity of n over 2 to the n minus 2, we would get infinity over infinity, which means that this is L'Hopital already. So I'm going to use L'Hopital's now. And we get the limit as n approaches infinity of 1 over 2 to the n times the natural log of 2. And substituting in here, we would get 1 over a really tiny number, or really big number. And 1 divided by a really big number makes a really tiny number. This is almost infinite. So the result is going to be 0. Therefore, we know that this converges. Is there another way I could have done this without L'Hopital's? Did any of you think about your relative growth rates? Hopefully when you look at this, you think, oh, you know what? I could do relative growth rates. So if we used relative growth rates, which grows faster? In the original problem, we had the limit as n approaches infinity of n over 2 raised to the n minus 2. We know that 2 to the n grows so much faster, which means the limit has to be 0, and therefore converges. All right, what about the next one? How many of you use L'Hopital's? Can I tell you I wouldn't have used L'Hopital's on this one? It's doable. We can certainly use L'Hopital's, but we're going to have to use it more than once because it's going to keep giving us the indeterminate form. So better would be to look at those powers just like we did up above. And if we look at these, really 3n squared and 2n squared are the only things that are impacting this problem. And when I do the limit here, the limit as n approaches infinity of this function, I'm just going to write a sub n, we're going to get 3 over 2. So therefore this converges. So lots of techniques to be able to determine if a series has a limit or if series converges or diverges. Now, we also have to consider sequences where it may not be possible to determine the limit, but we still need to know whether it converges or not. So let's look at some examples. Okay, before we look at these next few examples, this theorem that can help us, we have to get some vocab out of the way. First, a monotonic sequence. A monotonic sequence is something that constantly increases or constantly decreases. And I don't mean it goes up by the exact same amount every time. I just mean it continuously goes up. It continuously increases. And a bounded sequence. A bounded sequence is a sequence that has an upper or a lower bound. Sometimes it can be bounded by both, upper and lower. And that would be a sequence that we just called bounded. Otherwise, if we say it's bounded above, it means that every term in the sequence is below a certain number. Or if we say it's bounded below, then we mean there is a bottom number that nothing goes below and everything is above it. Okay, so here's a theorem. If we have a sequence that is both bounded in some form, above or below or just bounded in general, and monotonic, then it converges. So there are 3 things we want to look at, or 2 things we really want to look at. We want to look at whether it's bounded, meaning is there one place that has an upper limit? is it monotonic? And by determining those two things, we'll be able to see how or if this sequence converges. So the green dot in each of these represents a starting point. Nothing can go above or below the green dot unless the dots are continuing to be above or below. So for example, in this first one, it's green on my screen. Obviously your hand printed worksheet is not going to be green. But if we look at this example, this dot is the highest dot we've got, and everything goes below this. So we would call this bounded. So it is bounded on the interval from 0 to 3, 3 being the upper limit. Now, is it monotonic? And the answer to this is yes, because it's decreasing the whole way. Each value is a little bit less than the value before it. Therefore, we can say this converges. Because it's bounded and monotonic, it converges. So, hit pause, talk to your neighbor, and see if you can determine if these next three sequences are convergent using the idea of bounded and monotonic. All right, this next one to the right, is this function bounded? And this can be a little bit tricky, but based on the way the dots are going, I would say that this, yes, is bounded. And this is bounded with the low end being 6 and the low end being 3 and the high end being 6. Is it monotonic? Yes, every dot is a little bit higher than the dot next to it. Not by a lot, but by a little bit, so it's increasing. So we would say this converges. All right, what about this third one? Hopefully when you look at this third one, it becomes pretty obvious that this one, is it bounded? Yes, I would say that this is bounded because it's going between -1 and 1. It's bouncing between them. But the very fact that it's bouncing tells me that it's not monotonic because it's going back and forth. This is oscillating, so it diverges. We even said an oscillating function was not going to converge. So there was another thing we could look at. What about the fourth one? Well, the fourth one is a problem because it's not even bounded. It starts at 1, we'll call that, and then appears to go to infinity. Each value gets a little bit higher from the one next to it. So it is monotonic, it is increasing, but it's not bounded. It just keeps going on and up and up and up and up. So therefore, we would say this diverges. So this is the very definition of a sequence, an ordered list of numbers. We can find limits with sequence. We can still go through the whole idea of L'Hopital's, but this is a sequence. So tomorrow we're going to focus on, the next time I see you, we're going to focus on series and what that means. So have a good day, and we'll see you soon.